Good afternoon, my fabulous chemistry students. Video number 8, acids and base titrations. We will cover today neutralization reactions. Those neutralization reactions we use in a titration calculation. So there will be a little bit of math in the unit in today's video. Might get a little long, but I'm going to tell you the two things that are very important. We're going to cover them both. You're going to need to be able to do both of them. When acids and bases react, we know that they produce a water and a salt. That is our neutralization reaction. So let's get right into it. The neutralization reaction, when I'm neutral, I have equal amounts of the ions. So what I end up forming is a water and a salt. So the general reaction, acid plus base, always goes to water and a salt. Or I could say a salt and a water. The order is not important. And here's how it works. It is a double replacement reaction. The acid, the H plus donor. The OH, the base is the OH donor. If I take the H and the OH and put it together, I can rewrite that as water. And the Na and the Cl are going to form, remember we always do the positive ion first. I'm going to make my salt. So, in some reading and writing, with no writing, it talks about what's happening. The neutralization reactions are always a double replacement reaction, which we know how to do. And we always write the positive first and then the negative, but we need to be able to balance them using the crisscross rule. Okay? So everything we've learned, or many of the things we've learned in chemistry prior will come back into play. So let's start first with our HOH. That's going to make H2O. And that is balanced because now I have technically a +2 and a -2, so that's all good. And then I have KBr. KBr, I know Br is a -1 and K is a +1, so that is balanced, and we are good. Let me skip down to 3. Here I have 3 H's with an OH, so I'm going to make H2O, but I count 1, 2, 3, 4 H's. So 4 H's, I need to multiply this thing by 2. Okay? And then I'm going to have KPO4. And it's going to be K written first with PO4 phosphate. And I need table E for this phosphate. Remember, when in doubt, check E out. My polyatomic ions, it says phosphate has a charge of, where are you, Mr. Phosphate? PO4 is a -3 charge. K is a +1 charge, so when I crisscross down, this becomes K3PO4. And this is not correct. This bottom one is. On the right-hand side, I have 3 Ks, so I need 3 Ks. Let's see, I have 3 OHs. Here I have 2 OHs. What's going on? Gotta balance, gotta balance, gotta balance. So let's see, this is gonna have to be 3. Remember, this is HOH, so you know what, the easiest way to balance these guys, if it starts getting a little trouble like this, do it like this, do HOH. It's the easiest way to balance it, because here I see I have 3 OHs, so I need 3. Here I have 3 H's, I have 3, so now we're good. It's easier to see it that way. HOH can be written like this. I have 1 PO4, I have 1 PO4, and so now I'm balanced. Cute little trick for balancing equations with water if they ever get a little bit tricky. I'm going to do number 4, and I'm going to leave you with number 2. I can help you with 2. Remember, there's your water. All right, so I'm going to have H go with my OH. I'm going to write it just like that, HOH. And there are 2 OHs, so I'm going to need a 2 in front. Then I'm going to have my Ca with my NO3. NO3. I know that Ca is a +2 charge. and NO3 in table E is a -1 charge. So when I crisscross them down, the 1 goes to the Ca, the 2 goes to the NO3 to build a stable compound. And now I can recount 1 calcium, 2 NO3s, 2 NO3s, 2 H's, 2 H's, 2 OH's, 2 OH's. We are balanced. And I've made a salt and water. Okay, good. So let's remember that we can split that H2O up into HOH sometimes to make our balancing go a little easier. Now, it says here we do not always get a completely neutral solution. We will not spend a lot of time with this, but I'm going to work us through it. If I dissociate 100% here, and I dissociate 100% here, my acids and my bases, my H's and my OH's will completely form into water, and I will be neutral. And so I will have a pH of 7. Here, a strong acid, I dissociate 100% into HOH, or I'm sorry, into H and my other piece. My weak base will not. Let's say I do 50%. So now 50% of my H pluses are left over. Or that does not look like an H plus now, does it? I'll have 50% H pluses left over because 50% of them are going to hook up here and neutralize into water. I'll have 50% of my solution is H plus, so I will be acidic. And I will therefore be less than 7. And the exact opposite happens here with the strong base. I'll be 100% OHs. And here with a weak acid, I'll say, let's say I'm 50% H plus. That's going to use up 50% of this OH and leave me with 50% OH in solution. Okay, so I'm going to be slightly basic, and therefore I'm greater than 7. This particular piece is just to teach it so you know it kind of thing. This is where we get back into it. So neutralization reactions, and now this titration is what you are going to be held accountable for. We use these titrations to calculate the concentration or molarity of an unknown acid or base. So in lab, in the burette will be a base. In the titration, when I get to neutral, I will know that H plus equals OH minus concentrations. Okay, and that is what we call the equivalence point or the end point of the titration if I look to get the color change. So here is an example. I have this burette, and this is the burette. It's like a graduated cylinder that's upside down. So I know my starting volume of base. Can't spell very well. And I know my ending volume or final volume. Of base. If I subtract the two, final minus initial, I can get my volume of base. Down here I have an unknown acid, and when the color changes, I can then start my calculations. What I do have here that is known is the milliliters. I can measure how much acid I put down there. Okay, so milliliters is volume. I'm going to get that from the burette, and I'm going to get that from a graduated cylinder or something here with the acid. I usually know the molarity of the base that's in my titration or in the burette. What I don't know is the molarity of the acid, and I'll use this equation, MAVA equals MBVB, and plug and chug that out to figure out what it is. So I'm going to do the 2 example problems for you, and then we'll call it a video. There are a bunch of these in the practice packet, and you're going to need to do them because this is the math piece, and you need to be able to get it right. So it says, what is the concentration of a solution of HI? HI is acid. So what is the molarity of the acid, Ma? If 0.3 liters, so Va, I'm going to fix this A, make it little. It's supposed to be little a. Ma, we don't know. Va is 0.3 liters. And I have a Vb of 0.6 liters and a concentration of base equaling 0.2 molar. So now it's MAVA equals MBVB. So I plug this in. I have MA times 0.3 liters equals 0.6 liters times 0.2 molar. I see right off the bat to get MA by itself, I have to divide by 3.3 liters. And when I divide liters by liters, they cancel. So I'm left with molarity, which is what I want. Here, though, you do have to do the multiplication first. PEMDAS, multiplication before division, 0.6 times 0.2 equals, divided by 0.3 equals 0.4 molar base. Simple plug and chug. Identify my variables, plug them into the equation. Oh, there's 4? Oh, look at this. I do too, and you do too. I love it. I love when a plan comes together. What is the concentration of hydrochloric acid? I don't know the concentration of my acid. In a solution at 50 milliliters, so volume of acid. Oh, and that's volume of base. Okay, so here's where we got to do some reading, right? What is the concentration of hydrochloric acid in a solution if I have 50 mils of 0.25 molar KOH? So KOH is the base. I know it because of the OH. So I get there I'm given the molarity of my base is 0.250. The volume of my base is 50 milliliters out of the burette, and it neutralized 20 milliliters of the acid. So here, two things I want to make clear. I can use milliliters if they're both milliliters. I can use liters if they're both liters. First off, I don't have to convert if they're both the same. If one of them is different, then I do have to convert so that they're both the same. I have to compare apples to apples and oranges to oranges. Next, in the sample 2, we have to be careful how we read the problem and assign our numbers to the right variables. That might be the toughest part of this. So now I can plug in my variables to my MAVA MB VB equation. MA times 20 equals 0.25 times 50. I'm going to bypass the units this time because you know that they work. You know I should never do that, and I harp on you guys about units. So now again I have to do the multiplication first. 0.25 times 50 equals, divided by 20 equals 0.625 molar is the molarity of the acid. Let me just look at these problems real quick and see if there's any issues with you being able to solve them. Okay, so here it gives you the two concentrations. You're solving for the final volume. Okay, so the volume of the base will be required to neutralize it. So you're solving for the volume of the base this time, which is not any real big difference. 50 milliliters. Again, solving for the volume of the base. So now we're just solving for a different variable, but it's still just plug and chug. And it's been long, so I'm going to call it quits for me. You guys finish those two problems and you'll be done with your homework. And there's lots of practice in 7 and 10 on neutralization reactions and this titration equation. So notes are done. Sorry it ran long, but these are probably the two most difficult topics, especially with the math that we're going to deal with this unit. So I want to make sure you guys got a solid foundation. See you in class tomorrow.